I'd like to thank the organisers for the opportunity to speak here. I really appreciate it. And what I'm going to talk today is about a certain tool that I'm developing in a joint program with Fed and Nazarov. And what this concerns is the never mind. So this concerns the study of certain objects in order to try and find geometric conditions on a measure that are inherited from the boundedness of an associated singular integral operator. And I was contemplating whether to do kind of a survey or focus on one particular result, and I decided to do one particular result because it would enable me to kind of discuss more about how these things come into practice. So we're going to be working today in RD, and our singular integral is also going to have a dimension that's strictly smaller than D. And we're going to be interested in the case where we're dealing with a kernel, which is the S-Reese kernel, which is the following integral kernel. Okay? So what's the condition on the singular integral that we're going to be interested in? It's its L2 boundedness. So let's let mu here be a non-atomic measure. And we're going to be interested in the following condition, which I guess I'll call L2 bounded or something like that, which will be that the supremum of delta greater than 0, and then the integral over RD, integral over RD as well, with that k, it's a little awkward, so let me write it like this, times this quantity here, just to take out the singularity that's possible, s plus 1, and then this is f of y d mu y. So the convolution operator, but just taken out the little point at delta here, d mu x is less than the constant times the L2 norm of f d mu, right? So that's what we mean by L2 boundedness, just that the convolution operator of f mu is bounded in L2, but you just don't have to be a bit careful about the thing. Right, so the question that we're interested in is, what are the conditions on a measure? What does this imply about our measure mu? Okay, so it first came about from studies of removable singularities of certain PDE, but now it's kind of a question, I think, of its own right, which I won't say anything more about anything else about it. So what does this say about mu? Okay, so there's a simple condition. And that is that the measure of a ball can't grow too fast. So it should grow like r to the s for any ball. Okay? But this condition doesn't approach kind of necessary and sufficient for that. So we would like more refined conditions. And they split into the case of whether s here is an integer or not. So more refined conditions. So there's the case when s is an integer, which should correspond, and I'm not going to be talking much or anything about this, so I'll just be vague about it. And it's that if you enforce that your measure be s-dimensional in a sense, then the support should be quite smooth. So it should have some regularity. It should be rectifiable. So if mu is s-dimensional, so e.g. the Hausdorff measure of the support is finite, then support mu is S rectifiable. So this isn't known for all S, right? it's open for some. So this is known in two extremal cases. This is known if S equals 1, and it's there's a number of people who I should mention here. So in the case when your measure is regular, this is work of Mattia, Melnikov, and Vadera. And I should also mention work of David and David Mattia. And there's also S equals D minus 1, which is more recent work of Nazarov, Tolstoy, and Volber. Okay, and feeding into both of these is the work of David and Son. Okay, and making progress on the intermediate cases is one of the trickier problems in the field. Okay, so this is very interesting, much more interesting than what I'm going to talk about. I'm not going to talk about it. Okay, so the second case is non-integer S. And essentially, the condition is that that the growth condition up there can't occur too often. Okay, so there's nothing like a rectifiable set in non-integer dimension. So for S not an integer, it should be that the condition mu bxr less than cr to the s is not tight too often. So it's not often that you get a reverse inequality with a different constant. Okay. So there's a few results that I should state here. Let me just start by stating what I'm going to prove, and then we'll see how it relates to the literature. Okay, so theorem. So if S lies between D minus 1 and D, then there exists, oof. I should put it here. And mu satisfies the condition of L2 boundedness, then there exists some p between 0 and infinity such that, let me put it this way, this potential here is bounded. Right. So the constant p here depends on S and D. Actually, p here depends only on S and D. The constant also depends on the least transform bound in the stuff. Okay. So this says that this bound here can't happen too often because it has to be summable, right, almost everywhere. So let me just say a couple of things about how it relates to the literature. So I should discuss, there's a paper for S between 0 and 1. There's a paper by Matteo, Pratt, and Vadera, where this is proved with p equals 2, and that is sharp. Right? It's necessary and sufficient for boundedness in the sense in which these things can be, which says that if you restrict the measure on a set which is almost the same measure as the original one, then the resulting, that restricted measure is L2 boundedness. That means the resulting capacities are equivalent, which is how these things are stated usually. Okay? So that's one result. So this came after a qualitative version by Pratt. So qualitative version. And what this says is the following. So if we have this L2 boundedness holding, and the Hausdorff measure of the support of mu is finite, then mu is identically 0. Okay? So this is a qualitative version of this. Why is it qualitative? Because since under our assumptions, the lim sup of R tends to 0, mu b x r over r to the s is positive, mu almost everywhere. Right? Any measure which satisfies the growth condition and has finite Hausdorff support satisfies this. The bit where that is 0 has null Hausdorff measure. Okay? Well, the mu is 0. Okay, so this qualitative version was proved for S between 0 and 1 by Pratt, and S between D minus 1 and D by Eiderman, Nazarov, and Volberg. Okay, and this paper here was the catalyst for this guy. It follows the same scheme of proof. Okay? All right, so there's one more paper I should mention. I feel I might do this a few times today because my writing's very big. And that's by Regularity and Tulsa. And then we'll get down to a proof. Okay, so the next paper I'll mention also lies between D minus 1 and D. And it's Regularity and Tulsa. And they showed that this estimate here holds. They proved P equals 2 when the support of mu is uniformly disconnected. So what that means is that it's like a fractal set where you're built on a finite level and the sets are distributed according to their length. The important thing here is that this set's not necessarily S-dimensional. So it basically it says that it's what happens if the boundaries don't play a role. Okay? So this also kind of follows this thing, but incorporates some very deep ideas in its own right. And Tulsa communicated to us there might be some further developments here, but we can ask Maria about that if need be. Okay. So that's some history. In fact, actually, I've only covered the case where S is equal to 0, 1 and D minus 1. It is open in general in the meantime, but there is one result for all S, and that's by Vittler. So if you have this, then Vittler proved that this L2 boundedness implies that mu is not Alfors-David regular. So you can't have this lower bound. Right, all the time. She actually proved more. She proved that you can't have a set of positive measure upon which this lim inf is strictly greater than 0. Okay, so she proved more, but it kind of comes down to that fact. Okay. All right. Let me rub this whole board off, actually. All right. Okay, so we want to prove this theorem. And so, let's see how. So the first thing I want to do is just quickly discuss how to make sense of a certain bilinear form. So there's no originality in what I'm doing here, but we'll need to make sense of a certain bilinear form under slightly weakened conditions on a measure than is completely standard. Okay? So for this purpose, let's let mu be just any measure that's non-atomic, right? I'll be imposing much stronger conditions than that in a moment. And what we want to do is we want to make sense of the following thing. So let's say phi here is Lipschitz and compactly supported in RD, and phi has mu mean 0. Okay? And I want to make sense of the following object. Right, R mu phi integrated against 1 mu, right? So that's the object I want to make sense of. How should we do it? Well, let's let, say, phi be another Lipschitz compactly supported function, which is identically 1 on a neighborhood of the support of phi, right? And then we will write this as 2 terms, okay? So we write R mu phi 1 as the sum of R mu phi, psi phi plus R mu psi 1 minus phi mu, okay? And what's the best case in which one can make sense of this object? Well, we'll use anti-symmetry here, and so we will define this object in the following way. Right, so R mu phi psi, mu is defined as the following double integral. So we have kx minus y, and then we write this as 1/2 the following thing. So what do I have? I have psi x phi y plus the other way around. No, minus the other way around. Let's do it this way around. Let's do it properly. All right, and then minus psi x phi y. D mu x, d mu y. Right? So that's how we'll define that object. So why is this good? So this guy here is Lipschitz continuous on RD cross RD, and it vanishes along the diagonal. So we have a nice estimate of this guy, like some constant that depends on phi and psi times x minus y. Okay? This kernel's like negative s. So in order to make sense of that, I would like the function xy that goes to 1 over x minus y to the s minus 1 to be an L1 mu cross mu. And if it's true, I can make sense of this object in that form, right? So for this second term, what do I need? So what do I notice? So since phi has mean 0, psi has mean 0, we have a nice estimate on the support of this function, right? So this is, we have an extra bit of decay than we usually would outside the support. This is like in terms of mu and psi here. And this is on the support of 1 minus phi. Okay. So we have that nice thing. So in order to make sense of the second term, we need that the following integral be finite, right? So if we have these two conditions, we can make sense of this object, okay? And if we have some quantitative control on these two conditions, this object will have nice weak continuity properties as well with it. Okay, so we'll come back to that in a minute. There's one last thing here that I should mention, and that's the following: that if in addition we have that mu is finite and our L2 bound holds, we have a nice control on this, where this is the L2 bound times phi L2 psi L2 mu times the square root of the mass of mu in RD. Okay, so in the case where you have an L2 bound, you have this. This is not such a tough thing. You just pass to the limit in the previous expression that we had. Okay? Perfect. So that's just something we will return to momentarily. Okay. So, it's over here. All right, so, so for this, unless the measure of the space is finite, it's indeed not such a difficult statement. But if the measure is infinite, what you can do is if you restrict your measure to a ball, then the L2 bound is retained, right? And so this you then obtain by just restriction a locally finite version of this, okay? So there's no harm in it. But indeed, we're going to do a lot of limiting processes, and inside we will lose finiteness of the measure when we do that. So at a certain point, all measures will become necessarily infinite in the talk. I don't have quite the same knack for this as our speakers did yesterday, I fear. All right. Fair enough. Okay. So how do we prove the statement I just spent 10 minutes rubbing off the board? So we're going to prove a dyadic version of it, because that will make our lives a little easier. Okay? So we let D be the lattice of, in our case, open dyadic cubes. Okay? And what do we want to show? We want to estimate a quantity like the following. So let's say mu of 2q divided by L of q to the s. Oh, sorry, s to the power p. Mu of 2q is less than this guy. Okay, so that's our aim to prove a thing like this. Right? So, how to do it? Well, we're going to introduce a nice wavelet system. That's a nice way to do this. So we will define for some a greater than 1 a nice system of functions. So let's call it a mu q. And what will this be? This will be the collection of those functions which are Lipschitz with compact support inside this ball here, such that the Lipschitz norm, I will scale it so that it's all nice. So the homogeneous Lipschitz norm is less than or equal 1 over the length, and their mean should be 0. Okay? Where this xq here is defined so that xq plus L of q times 0, 1 to the d is equal q, right? So kind of the bottom left-hand corner, whatever that should be. Okay, so so that's the system we'll have, and it's not surprising that this is a nice kind of wavelet basis in the following sense. So for any g in L2 of mu, I have that the sum over those dyadic cubes of the inner product with G phi q with respect to mu squared divided by, let's say, mu b xq, and then 3a lq. This guy should be bounded by some constant a g squared L2 mu. Okay, so this is just an exercise just to do this, expand it out. The dual formulation's a little easier in terms of the sequence, but it's just an exercise to see that. Okay? So what does that tell us here? Right? So thus, for any choices of our phi q in our this with a fixed, we have a nice bound of the following form. So the inner product of the Riesz transform phi q, let's say, 1 mu squared over the measure xq3a lq here, this guy should be bounded in terms of just the measure of rb. Right? So informally, what am I doing here? I'm putting r mu onto that rather than that, which is allowed because it's just antisymmetric. And then I'm using this result along with the L2 boundedness of r mu. Okay, and I end up with this. Okay? So I look and I see what's the difference between that and that. Even if you want aiming for a 2 here. Okay, so what's the difference? So so this is using this L2 boundedness, right? And just anti-symmetry. So I can put R either on phi or 1. Okay? So, oh no. This again. Okay. While I'm here. So essentially, what we want to do is pick up the instances when this guy's non-degenerate. Right? So if we could say that this guy was non-degenerate for some choice of phi q, we would end up with something like our potential, which is what we want. Okay? So if, and this is a big if because it's not true, if we could show that there exists some parameters, let's call them delta greater than 0, a greater than 0. I always miss one out when I'm doing this. No, I think that's okay. Such that for all cubes in the dyadic lattice, there exists some function phi q in this nice space of test functions such that if I had a nice degenerate lower bound here, and what should my lower bound be of the form? So if I'm not going to square it, I should have mu 2q squared over L of q to the s. Right, so if I have an estimate like this, if I had it, as I say, we don't have it, but if you did have it, what would it tell you? So then, we could plug that into our left-hand side here, and what would we end up with? Something along the lines of mu 2q squared over L of q to the s times mu of 2q divided by this guy times mu of 2q again. This is less than some constant times RG. Right? So the difference is this thing. But you can average over dyadic lattices, and this thing wouldn't be a problem on average. And so you could get rid of this thing if you wanted to. Right? That wouldn't be an issue to get rid of that. So if this was true for all cubes, you would arrive at the sharp p equals 2. Okay? Which I didn't claim, but that's what you have. And the reason is because this is false for all cubes as stated. Okay? You can arbitrarily well approximate the Lebesgue measure on certain scales while preserving the growth bound. So for any delta, I can beat this. Okay? I can make it smaller. So we don't claim that this holds for every cube, but we claim it holds for a number of cubes, and that number is sufficiently well, there's enough of them to get it with a power. Okay? So we will show that this guy here, let me call it dagger, that dagger holds for regular enough cubes. Okay? So what do I mean by regular? I now need to return to my dyadic lattice and give it a graph structure. Okay? So let's endow D with a graph structure. Okay? So the only problem with not just saying that the parent is there and your dyadic siblings, you attach dyadic siblings, your dyadic parent and your dyadic children, is that just there's some places where you have infinite distance between two cubes, right? So in the most blunt way possible, rule this out in any way you want, right? Here's one way to do it. So each cube is adjoined with neighbors of same side length also its parent and its children. Okay? As they're open, it only has one parent, right? So then you can define the distance between two cubes as the shortest path, right? Okay, is that reasonable? So you just go through neighbors up and down, that kind of thing. Right, so what's the degree? I don't really care, but it's bounded by, say, 1,000 to the d. Right? That's a crude overestimate. I think 4 or 6 would do, right? But 1,000 certainly right. Okay. So then, what's a regular cube? It's one that really has kind of logarithmic growth in the side length. Okay, so you allow it to, well, its density is almost maximal, I should say. So, an epsilon regular cube, Q satisfies the following thing. That, the following quantity, so Q prime here is any other cube, okay, is less than e to the epsilon dq q prime times mu of 2q divided by L of q to the s for all q prime in D. So for every other q prime, I have this quantity, right? And our main proposition is that there exists epsilon naught and then delta and A such that if Q is epsilon regular for epsilon less than epsilon naught, right, it just decreases in epsilon, so it's no big. Then I do have my dagger. Then dagger holds. Okay? So that's our main proposition. Okay? So I will return to the proof of this in just a minute. Let me just make a couple of comments about how the theorem follows. Okay? So thus, combining this with our previous work, what do we have? We have that the sum over Q being epsilon regular of, this is the L2 boundedness, implies that the sum over 2Q over L of Q to the S squared mu of 2Q is less than some constant times the mass of RD. Right, so that's what our L2 boundedness yields, just over those epsilon regular cubes. This guy, by its definition, is doubling, and so that 3A thing disappears to the right. Okay? So that's what we get. So the question is, when does the sum over all cubes get dominated by a constant multiple of the sum over the regular ones? Right? So if our P here is greater than what do I need it to be? Essentially this degree, right? Let me call it D. Okay? Yeah, D will do. All right, so let's say D plus 1, right? Then it is not hard to show that the sum over all cubes, not to the second power, but to the qth power, is bounded by some constant times the epsilon regular ones. Oh, and there should be an epsilon here, and it's that, right? So epsilon times P should bound it. Okay? But we already know that the L2 boundedness implies the growth condition, so if P is very large, putting a 2 there only increases the size up to a constant, and that yields the theorem. Okay? So this is true merely because if you just do some simple graph theory, really, you look for a given cube, and then you can, by a simple maximizing argument, show it's related to an epsilon regular cube, and then this condition tells you that everything else has exponential decay. Okay, so that's how that follows.
You just need one epsilon here.
What? Yeah, so we just need one epsilon. Yeah. So I could have just said this epsilon 0 regular and just had that, because really, if it's true for some epsilon, it's true for any smaller here. Okay? All right. So now to get onto the heart of the matter, which is this proposition. Okay? So let's prove it. Uh-oh, I think too much water there. So essentially, it's going to follow by a big compactness argument. And that's where our notion of a reflectionless measure is going to come in. So with any luck, I'll talk about the subject of the title at any point, at some point during the talk. All right. I actually did this as a summer job to people's windows. So if you're noticing expertise here, then all right. So okay, right. So proof of the proposition. Okay. So suppose not, right? Okay. So the main thing is to look at how this guy rescales. Okay. So how do I want to rescale my measure which satisfies the thing that's dripping up there at the top? I want it so my cube Q is the unit cube. Okay. So what does that mean? I want to consider the following measure. Right, so that's the measure I want to consider. Okay? So if Q is epsilon regular here, where this being the variable that you would put a set in, right? So what does this satisfy? So mu of 2Q is equal 1, right? And what do we know about it? So the fact that we've divided by the measure here means that we've lost all quantitative control on the Riesz transform bound, which scales like mu squared on the left and like mu on the right. So we've lost control on that completely. We can't use that anymore. And but what can we do? We know that the mu measure of any cube Q prime doesn't grow faster, or even 2Q prime, grows no faster than its distance Q prime to the unit cube Q0 times LQ prime. That's just rescaling this top condition here. Okay? So this is the condition that we now have. Okay? And I want to show that R mu tilde, oh, sorry, I put it in the wrong place, phi 1 mu tilde is bigger than or equal some delta, an absolute value. Right? So why does I rubbed it off. Right, so what was dagger? It was that R mu phi 1 mu is bigger than or equal to delta times mu 2q squared over LQ to the s. Right, so that's what that condition was. So how does this scale? 2 mu's on the left and 2 mu's on the right. So when I take mu tilde, that goes and that's nice. And this LQ of S gets mopped up in the kernel when I do the change of variable. So everything comes to the right? And now this function phi should just be from the set where Q was Q0. Okay, and the Lipschitz norm scales in the right way. So we're interested in this. And So I'll say now that any measure that satisfies this, we will call reflectionless. Okay, so that's our definition of a reflectionless measure. So it can't detect itself on the support of the measure in this weak sense using nothing but the operator. Okay. So now let epsilon tend to 0, and we get a reflectionless measure measure mu. So it satisfies this condition with the growth of any cube q prime, or even twice it, not exceeding just the length of q to the f. Right? So that's what we get as a result of supposing it's not true. That's how a result, that we get a measure. We've recovered the growth condition, and it's there. And so our main result is really these measures don't exist if my S here lies between d minus 1 and d. Okay? And then rolling our way back.
So you have some nice practice.
Yeah, so it's because the result that you have is that, say, if mu k tends to mu weakly, which means testing it against continuity, so really weak start, right? And you have that fk tends to f, and I probably will put too much thing on here. So if fk, if their Lipschitz things are bounded by, are compactly supported, and they're supported uniformly in some ball, and also they have mu mean 0, then R mu k fk 1 mu k converges to R mu f1 mu. Okay, so we just use that again and again and again and again and again, and that's what you get. Okay, so, and that's just the fact that I have some quantitative extra on the bilinear form conditions here. Okay, so this is what we need to prove and what we prove. Okay, and this is really where the work starts. So this is the non-trivial part, because so far I've just done little L2 things, right? Nothing difficult here. But this you actually need to do some work. Okay, and this should be true for all S non-integer, but the reason why we only have it here is because we have the strong maximum principle. Okay, can I have 2 minutes just to say a few words? So a few words about this. So now we need to work with a pointwise representative of our Riesz transform, right? No more of this bilinear form nonsense, right? So we want to consider some nice pointwise representative of this, right? And what is this really? So you can think of it really as R mu of 1 minus the integral, or let me say the inner product of R mu 1 phi mu, where this guy has integral 1 and is fixed Lipschitz function with compact support. Okay? So you're just subtracting an integral average, right? So this makes sense because you really think of this as a cutoff plus the rest. The tail then cancels. This measure here is necessarily infinite at this point. So the tail then